Hi, this is Tim Chu from San Jose State University. I'm here today to talk about maximum and minimum values. I'll first start off with the definition of maximum and minimum, and especially focusing on the tricky part, which is the question of what does x being near c mean. I'll talk about the extreme value theorem, Fermat's theorem, and then finally I'll finish up with an algorithm. Yes, an actual recipe about how to find absolute minima and maxima on a closed interval. So here we go. So first of all, let's start by defining what the problem is. So with the definition of minimum maximum. So suppose f is a function with domain D. So to prevent us from floating off into the ether and being totally abstract, what you want to think is that D is either a closed interval a b, or less commonly D might be an open interval a b, or the entirety of the real numbers. All of the real numbers are. But really, just want to think the main case you want to think about is when D is a closed interval a b. All right, so here's the definition. So for C in D, to say that f of C is an absolute maximum value of f on D means that for all x in D, f of x is less than or equal to f of C. That means, if this is where f of C is, you think about this in terms of the graph, then for every other point in the domain of f of x is lower. So it's kind of what you'd think, that's what it means to be an absolute maximum. So now here's a puzzle. Here's an exercise for thought. What do you think the definition of absolute minimum is? All right. Hopefully you paused the video and thought about it for a minute and figured out that what the definition of absolute minimum is, which is that for C and D, to say that f of C is an absolute minimum value of f on D means that for all x in the domain D, f of C is less than or equal to f of x. So it's exactly the same thing, except switching f of c bigger than every other value to f of c is smaller than every other value. So absolute maxima and minima are sometimes called global maxima and minima. So the definition of local maxima and minima is more subtle. So what does it mean to have a local minimum or maximum? So that is for c in the domain D, to say that f of c is a local maximum value of f means that for all x near c, f of x is less than or equal to f of c. So it's the same definition as before, except you're only worried about all the x that are near c. So what do I mean by near? Never mind what I mean by near. It means near. Oh, everybody knows what near means. It means near. Okay. Obviously, this is a tricky point, and so we will explain that more precisely later. But for now, just say, it means near. Well, everybody knows what near means. Okay. So for now, here's the definition of local minimum. And again, you should pause the video and try to see if you can come up with this yourself. All right, so again, for any point C in the domain D, to say that f of C is a local minimum value of f on D means that for all x that are near C, never mind what near means, f of C is less than or equal to f of x. And again, there's another piece of terminology. Local maxima and minima are sometimes called relative maxima and minima. Okay, so I think probably that was a bit off into the ether for most folks for seeing this for the first time. So let's get concrete and consider the following example with domain, the closed interval 0 to 5. Ta-da! There's an example. So here in this example, f has a local but not an absolute maximum at x equals 1, because look, there you can get a higher y value by going a little bit farther away. F attains a local and absolute minimum at x equals 2. So this is as low as you can go, no matter where you go, whether you stay close or you go far away. And f attains a local and absolute maximum at x equals 4. Again, this is the highest possible y value for y equals f of x, whether you stay close to x equals 4 or go far away. So, okay, so as promised, we're now going to get to the question of what does it mean to say that x is near c. So let me review what we were saying before. So for the definition of local maximum, so for C and D, to say that f of C is a local maximum value of f on D means that for all x values near C, f of C is greater than or equal to f of x. And so here, actually this is the trickiest part of it, depending on your class, there are two actual possible meanings of all x near C. Meaning number one, which is probably the more common one for a calculus class, says that if this is going to be true for all x near c, then there must be some open interval, some little tiny open interval from a to b inside the domain D, with c in that open interval a b, such that f of c is greater than or equal to f of x for all x in that open interval. So one upshot of what that means is that if you have an endpoint of your domain, that endpoint cannot be a local minimum or maximum. So here's the second meaning. This is less common for a calculus class. There is some open interval a, b containing c such that f of c is greater than or equal to f of x for all x that are contained both in a, b and the domain D. So in the upshot of that version of the definition is that endpoints can be local minima or maxima, and that every absolute minimum or maximum is always a local minimum or maximum. So note that these meanings of near differ precisely when C is an endpoint of D. The first, like I said, the first one is more common in calculus, and the second is often used in higher level courses. So again, that was probably sort of way off in the ether for most folks that seen this for the first time. So let's consider a following concrete example where with the domain 1, 5. So let's look at this point over here. This point is pretty clearly, I hope you can see the absolute maximum y value that this function can attain on the interval 1, 5. But is it also a local maximum? That's actually the subtlety in the definition in question. Well, in version 1 of the definition, which again is the more common one in calculus classes, where you have no local maxima or minima at endpoints, then f attains an absolute maximum at this point, x equals 5, but does not attain a local maximum at x equals 5. So that's a little bit weird if you think about it too hard. It's sort of like saying that you're the tallest person in America, but you're not the tallest person in San Jose. I mean, you're sort of globally tallest, but not locally tallest. So if you think about that too hard, it's a little weird. But nevertheless, it's one that's most often used in calculus classes because it makes the process of finding local maximum and minimum more straightforward. Here's the same example on the domain 1, 5 again. Again, the question of, in version 2, the question of, we have here an absolute maximum, is this also a local maximum? In version 2 of the definition, where every absolute maximum must also be a local maximum, then f attains a local and absolute maximum when x equals 5. You may find this sort of morally satisfying. It sort of makes sense. You know, if you're the tallest person in America, then you got to be the tallest person in San Jose, right? But on the other hand, you have to think a little harder to find all the local maxima and minima, and so often this is not the definition that people use, just because it makes the actual process of finding local minima and maxima more difficult. Anyway, so the upshot is this really will vary among different classes and textbooks, and you have to consult your instructor. But the rest of this video will use version 1 of the definition, where endpoints are never local maxima or minima. But please check out the examples in your textbook and check with your instructor to see which version of this definition is right for you. Side effects at this point in the semester may include dizziness, lack of sleep, loss of perspective, sporadic nausea, loss of reality, and hallucination of calculus formulas of everyday existence. All right, now we come to the extreme value theorem. Okay, so now if function f has a domain, a closed interval D, going from A to B, then there is a straightforward way to find the absolute maxima or minima of f on D, thanks partly to the following theorem, the extreme value theorem. It's extreme! The extreme value theorem. So let f be a continuous function with domain and closed interval AB, then there must always exist points C and D and AB such that an absolute maximum f of C is an absolute maximum of f on D, and f of D is an absolute minimum of f on D. All right, so here's a shorter, punchier version. A continuous function always attains at least one absolute minimum and at least one absolute maximum on a closed interval. So here's some examples. Look, it must be true, right? It works for these 3 examples, right? So we have 3 examples, of continuous functions defined in a closed and bounded interval. And look, there's always at least one absolute maximum, one absolute minimum. Done and done. Proof. All right, well, anyway. A few notes about the extreme value theorem. If you're interested in theory, the extreme value theorem actually lays the foundation for much of the most interesting theory of calculus. It's actually wicked hard to prove, as we say in my home state of Maine. It's super difficult to prove. After some experiments, you may believe it's true. Well, look, there's 3 experiments right there. It works, great. But it's actually almost false is the thing. A discontinuity at a single point can mess it up, and here's some examples. So here's an example of a function that is continuous except at one point, and it has neither an absolute maximum nor an absolute minimum. It gets closer and closer to the maximum and never gets there, and save from the minimum. Here's another example where you have a function that's continuous except at sort of the endpoints, and again, there's no absolute maximum or absolute minimum, and here, again, it is a function that's discontinuous only at one endpoint, and it has a global maximum because it's right there because the point sort of flies up above the rest of the graph, but there's no local minimum because you always get closer to a minimum but never quite get there. All right. Well, anyways, so that's weird, but you want to, we are mostly interested in continuous functions in a calculus class, and so we have this happy situation more that you see up to the top. All right. So the other key ingredient in finding absolute minimum maxima is a theorem known as Fermat's theorem, which says that if f has a local minimum or maximum at C and f prime of C exists, then f prime of C is equal to 0. In fact, we can neatly restate Fermat's theorem using the following definition. So definition, a critical number of a function f is some C in the domain of f such that either f prime of c is equal to 0 or f prime of c does not exist. And so here's a restatement of Fermat's theorem. If f has a local minimum or maximum at c, then c must be a critical number of f. Ta-da! So, so that's handy. So, and remember, the implication only goes one way, that if you have a local minimum or maximum at c, then c must be a critical number. It doesn't go the other way. So why is this true? So you may be curious, like, why should this be? I just thought I wanted to show you this neat little picture that maybe help you remember what Fermat's theorem says. So suppose that f has a local maximum at x equals c, and minimum would be the same, so we'll just look at maximum, and f prime of c exists. Ta-da! Well, this is what the picture looks like. So here's our local maximum, our sort of highest point nearby, for all nearby x, and we're assuming that f prime of c exists there. Well, if you look at the secant slopes to the left of c, those are positive, those are in blue, and so since f prime of c is the limit of those secant slopes, f prime of c must be greater than or equal to 0. And to the right of c, your secant slopes are negative, and f prime of c is the limit of those secant slopes as well. So f prime of c must be less than or equal to 0. So what's the only number that can be greater than or equal to and less than or equal to 0? Yep, it's 0. So f prime of c is equal to 0. Ta-da! Proof. Okay, so now we finally get to the algorithm of finding absolute maxima and minima on a closed interval. So suppose f is a continuous function with domain the closed interval AB. Well, on the the extreme value theorem says that f must attain an absolute minimum and maximum somewhere in AB. So there is an answer there somewhere. 2, any absolute minimum or maximum that is not at an endpoint must be a local minimum or maximum. And 3, Fermat's theorem says that any local minimum or maximum must be at a critical number. So it follows that we only need to check critical numbers and endpoints for absolute minima and maxima. And so here's an algorithm for finding the absolute minimum or maximum of a differentiable function f on a closed interval AB. 1, you find all the critical numbers of f in AB. Remember, those are all the points where f prime is equal to 0 or does not exist. 2, you plug those numbers back into f, those critical numbers back into f, to find f of c for all critical numbers c, and also all endpoints c, because remember, one of the things about not having local minima or maxima at endpoints is that, well, you have to do those separately, but that's just 2 more points to check. And the largest value you find in the previous step, in step 2, is the absolute maximum value, and the smallest is the absolute minimum value. And the point of all this is that calculus reduces finding the absolute minimum or maximum of a function on a closed and bounded interval, which in principle might be an infinite problem. It reduces that to a finite problem. All right, so that's enough for now. What are you waiting for? Go try some problems. Go do something useful. Thank you. Bye. Bye.